Welcome. Today's lesson, 7.8, modeling using polynomials. We're going to take and model real-world situations using polynomials. Typically, we're going to look at binomials, but we're also going to look at some higher-order polynomials as well. And we're also going to work on multiplying polynomials together using our product rule as we've been using in the Punnett squares as well. So let's go ahead and get started. Things we need to remember. First of all, we need to remember that the area is the product of the length and width of a rectangle or a square. Okay? Area is kind of that space that's in an object, okay? A two-dimensional object specifically. So let's go ahead and draw a two-dimensional object. This is a nice rectangle here. And we have a length and a width to this object. Now some people might prefer base and height. Either way is fine. Our area then, the area of an object is just going to be equal to its length times its width. The perimeter, however, is the sum of all the sides of an object. So not only do I need to know the length and the width, but I also know in a rectangle and a square that both lengths are the same and both widths are the same. So looking at that, I can say that my perimeter, I can express it in any number of ways, but I could first say my perimeter is my length plus my width plus my length plus my width. I can go ahead and combine like terms to give me 2L plus 2W. Or I can even rephrase that as my perimeter is 2 times the length plus the width. We'll probably look at more of this way throughout the process of working with perimeter today, but that is a binomial there. This is also another example of a binomial. We typically take our perimeter and combine our like terms. So again, area can be defined as the product of the length and the width, and our perimeter is a sum of all the sides, or 2 times the length plus 2 times the width. We're going to have to remember those as we go through today's lesson. Right. So our first thing is we're going to find the area of the following square. And we're given a square with a length and a width of 5x plus 5. So again, remembering our area is equal to length times width. And we know from our diagram that our length is equal to x plus 5. We know our width is equal to x plus 5 from the diagram, of course. So then I can rewrite my area as x plus 5 times x plus 5. Since it's a square, I could say x plus 5 squared, but again, we're going to expand, as we've talked about before, every one of our binomials or trinomials or larger number polynomial terms. We're going to expand those and put those in our Punnett square when they're squared or cubed or whatever. So we will end up now with our Punnett square. X plus 5 on the top. X plus 5 on the bottom. We're going to keep our training wheels on for just a few more days here. So I'm going to put my exponents of 1 here. I didn't see an exponent, so I assume it's 1. I'm going to write it down just so I remember. Now we're just going to use the product rule. And in the product rule again, multiplying coefficients, adding exponents. So we're going to have our x here. 1 plus 1 gives us 2, so we added the exponents there. X to the first times 5 would give us 5x. 5 times x gives us 5x. And then, of course, 5 times 5 would give us 25. From that, we look at our diagonals. Again, we see for our diagonals that it sure looks like 5x and 5x. They're not only like terms, they're the same terms, so we can combine them together. And our area then would just be equal to x squared plus 10x plus 25. The nice thing about this as a definition for our area is that I can then have a factor of saying that I started out with a square, a 5 by 5 square, and I want to find the area as I start increasing it by a length x. I can see how much area that would give me. And then if I wanted to, I could optimize it for the perimeter or the amount of fencing I might want to put around if this is a garden or something like that. So this formula is a little more flexible for our area than perhaps just saying tossing in regular numbers. Again, our area here is a is equal to x squared plus 10x plus 25. Moving on to our second example, it's the same basic concept, but now instead of binomials, I'm using trinomials. Again, I'm going to have to define what my area and length, my width and length are. So my area, again, is equal to length times width. I'm going to identify 3x squared minus 2x plus 5 as our width. Our length, we're going to say, is 2x squared plus x minus 3. And from there, I can write my area formula. Thus, that my area is going to be 2x squared plus x minus 3. I'm going to put those in parentheses. I'm going to multiply it by 3x squared minus 2x plus 5. Now I'm going to have to come up with a 3 by 3 Punnett square. So I'm going to extend my page a little bit here, so we have plenty of room to work with. What I've suggested as a hint to drawing these things, write out your first polynomial. From there, create your columns. Get plenty of space here. And then go ahead and write down the other polynomial along the side. So 3x squared minus 2x plus 5. This kind of gives us a little bit more room in these squares, and if I try to draw the squares in first and the Punnett square in first, it typically doesn't look as nice. So, all right, before I get started, let's go ahead and make sure all of our variables have an exponent. I see the x right here. I'm going to put an exponent of 1 on it. I also see this negative 2x here, and I'm going to put a 1 on its exponent. So now I'll remember when I add the exponents, it's not going to be 0 or 1 or something like that, but I'm adding 1 plus 1. Okay. In the upper the upper left-hand box, 3 times 2 is going to be 6. And then I add the exponents together of 2 and 2, and I get 4. The coefficient on that x to the first is 1, so 3 times 1 is 3. X squared gives me an exponent of 2, and x to the first gives me an exponent of 1. 2 plus 1 is an exponent of 3. And then I take 3 times negative 3, I get negative 9, and I bring over my x squared. Negative 2 times positive 2 is going to be negative 4. X, and then 1 plus 2 gives me an exponent of 3. Negative 2 times 1 is negative 2. X, and then 1 plus 1 gives me an exponent of 2. Negative 2 times negative 3 is positive 6, and I bring over my x to the first. Finally, in my last row here, 5 times 2 is 10. I bring down the x squared. 5 times 1 is 5. I bring down x to the first. And 5 times negative 3 is negative 15. At this point, now I'm going to look and I'm going to try to find my like terms. Looking at diagonals, I see that I have a like term right here. Negative 4x cubed and 3x cubed can be combined. I'll then look at my other diagonals and I see negative 9x squared, negative 2x squared, and positive 10x squared. So I can combine those as well. I yet have even another set of like terms, and that is going to be my 6x and my 5x. With that in mind, I can go ahead and add these together. Again, my upper left-hand box, more often than not, will be my first term, especially if I write everything in standard form. I'm then going to combine 3x cubed and negative 4x cubed. So negative 4 and positive 3 is going to be a negative 1. And again, exponents don't change when I'm combining like terms. Looking at my second group of like terms, I have 10, negative 2, and negative 9. That's going to be a total of negative x squared. Okay. 10, negative 2, and negative 9 add up to negative 1. So we get our negative x squared there. Our third set of like terms are 5 and 6. So that's going to be 11x. And then we're going to subtract 15. We look at this. I don't have any more like terms to combine. 4, 3, 2, and 1 for our exponents on x. They go from highest to lowest. So I've written this in standard form. And so my area, and we're going to write this in function notation. My area is a function of the value of x is equal to 6x to the fourth minus x cubed minus x squared plus or minus 15. That's part 1 of this lesson. Part 2, we're going to take the same principles, but now we're going to apply them to the real world scenarios. So please watch the second video for this lesson.